I sort of find this interesting in a historical perspective, having worked in the oil and gas industry for 28 years, some time ago, but what, 25, what? Could I just speak louder? Would that help? Testing? Is that working? Fascinating thing to me about that number is about 25 years ago, I used to have do these projections for the oil and gas business. Oh, 101,000 million barrels a day of production was sort of going to be a plateau level. And that same number was what we projected 30 years ago in the oil and gas industry, but we expected to hit it about the year 2000 or 1995. So what's happened is everything has slid, which sort of shows you the extent to which the energy markets go through lots of changes. And you never quite know what they're going to be. In this case, we've had a decline in demand, and we've had a much slower ramp up in production than people thought. We've also had a lot of changes because as you go out to meet that demand of 101 million barrels a day, conventional oil is only projected to provide about 65 million barrels a day of it. So all the rest of the oil production, in other words, 40 million barrels a day, is going to come from unconventional production and from natural gas liquids. That's a new world. That's not the same world that we were in 30 years ago when we talked about oil production. There are things like methane hydrides, which are long shots, but which some people are very serious about moving ahead with. If there were methane hydrides that really could come into the market, we would have more than enough gas to meet all the world's energy demands. The problem is those are frozen molecules that way down deep, and when you produce them, you have tremendous control problems on making that production. Are people trying to do that? Yes, there's been some tests in Japan. They've actually got a production well on where they brought it up and they're trying to produce it. And we've all known for years that the resources of methane hydrides are just huge. Renewables are going to provide nearly half of all the increase in global power generation. So the question is, and we know that unconventional came on and surprised us, so the question that this panel is worried about, well, what are the big surprises that are coming yet? And those surprises can come in many areas. And we're fortunate today to have three great panelists. I'm going to start with Cheryl Martin, who is Deputy Director of Advanced Research Projects at the U.S. Department of Energy, running the ARPA program. And I've asked her to try to identify 4 or 5 subjects that she thinks that the DOE is looking at today that could be game changers from the point of view of energy production. And then I will move on to Mr. Giovanni Santi from the European Commission, who runs their research into energy issues. And he's going to take a different slice at issues. And he's going to worry about what the systems impacts are going to have to be to run energy markets properly or even more better as we move out in time. And then we're lucky to have Dinu Patriciu, who is doing a tremendous amount of work in the Black Sea area and has got some very innovative and things that we want to talk about, and is going to give us a presentation on a whole different perspective on the kinds of things that may happen in the future that could radically change the world we live in. So, Cheryl, I'm going to start with you and let you give your 5-minute pitch.
Great. Thanks so much, Sam. Is this on? Can you hear me? Can you hear me now? No. Can you hear me without it? All right. How about we do that?
I think you have to give.
I think that's Does that work?
Yes.
Ah, okay. There we go. First miracle has happened of the day. And so RPE, like DARPA, is looking to push the envelope of technologies. And so we are not looking at technologies that you potentially will see in the market in the next couple years. And so what I'd like to do in this couple minutes is, but just let's imagine a different future. RPE's motto is changing what's possible in a couple ways, about reframing questions so that we get different eyes to the problem. Right? If you're banging up against the same wall all the time, what should you do? You should reframe the question. So maybe you still have constraints, but they're different constraints. So one that I think kind of captures people's imagination a little, we deal in fuels all the time with the issues of cellulose, right? Trees have been evolving, plants have been evolving for millions of years to be trees and plants and stand upright. So why couldn't you envision genetically engineering that plant to be more fuel-like and less plant-like, food-like? So things like porting the traits of algae into tobacco. So you could think about tobacco as a crop, as a fuel and energy crop. Or having a loblolly pine, these big pine trees that grow in the southeast of the United States, have high levels of terpenes. So you could have a tappable pine forest if you could get those levels up. And so you can vision that the world could be different. Maybe we'll have different constraints. Maybe you have to deal with that tree differently. Maybe you can have tobacco as a crop differently. But you've moved it away from the constraint you have today. So I think a couple others that are really important, I think, to this region, things we talked about a little bit at lunch. Ernie talked about carbon capture, right? I think the reality is we have to figure out how to capture CO2. And so there's a lot of technology. A lot of people have put a lot of years into the current technologies. But RPE put out a call a couple years ago saying, let's re-envision this problem. Let's go after this with a cost metric significantly lower than where we are today. And we had some teams come together to do demonstration projects with us, guys who had worked on supersonic engine design. So when you have a supersonic engine, you're basically shifting the flow of the air in order to get the thrust. When you do that, you do not want the liquid to solidify out because it'll blow your engine apart. It's a problem. But however, if you want to capture a flue gas stream, you want exactly that to happen. So can you use the design of a supersonic engine to put a flow in place that would allow the CO2 to actually spin itself out and so that you could capture it much more easily? No chemicals, very little CapEx. And so a small company called ATK in the US has actually demonstrated on a small unit that that is possible. And they just got funding from another part of DOE in the next couple years to go to a demonstration. And so really exciting. If you could get that, not only would it be lower CapEx, no chemicals, but it would be a footprint much smaller. And so you could really think about retrofitting current stock. Right? Those are some of the exciting things. And there's others like phase-changing materials and enzymes that could think about other ways of doing carbon capture technologies. And so we're very, very excited as those go to their next scale that we will see some things that could make sense in the future. And again, as we look to scale those, we would look to partners potentially around the world where that's of interest to be able to do those types of demonstrations. Another one that I think is really important, whether you're trying to integrate renewables, whether you're worried about resiliency of the existing grid, or whether you're worried about cyber, is the whole question of the grid itself, right? And I think we could talk about it from the conversation this morning. We talked about efficiency. Well, the fact is we generate a lot of electricity, be it in current gen or solar panels, and we lose a lot of it. Every time we shift its frequency, every time we go up and down in current level, we lose some of the electricity. And so we've worked a lot with all different types of things, inverters, transistors. We've had a number of small companies that have demonstrated off of a solar panel, University of Colorado at Boulder with NREL, one of the national labs, 25 to 30% improvement in the conversion of electricity off the solar panel. And so you think about those types of things across the spread of grid technology that we have today. It would truly be game-changing if we can implement some of those. So that would be just being able to get the electricity into the grid better. But then unlike the internet, the grid's not routable today, right? It goes wherever the path of least resistance. And so we've had some really interesting technologies. A company called Smart Wire Grid. Basically, if you think about a high tension wire, you clamp a magnet on it. And then you can induce into that wire belief that it's congested. And so what it'll do is push the electrons into other parts of your network. So then you can start to think about using these automatically to route your electricity. So again, you get rid of congestion, which is a big issue. You could utilize your network much more efficiently, and potentially you could route around outages. And so we have lots and lots of projects like that going on to think about the whole idea of could we actually have a true grid that was routable and intelligent. And then you think about things, the discussion about microgrids versus macrogrids. Well, there's enablers for that. Some of them I just talked about, but other things like AC power flow control. Right now, power only goes one way, right? If you've got a power flow control, it goes one way. Well, if you have two-way power flow control, you could have microgrids where their backup is the main grid, or a lot of other permutations of this. And so we're very, very excited about our partners that we're working with on these early stage technologies. And some of these they're demonstrating right now. So Smart Wire Grid with these magnets is out there right now demonstrating in Tennessee and in California, and also talking to folks in India and Indonesia and Europe about further demonstrations. And so some of you may be already experiencing some of that. So another big piece is storage. We've got lots and lots. A third of our portfolio is on storage, both transportation as well as grid level storage. And again, I think some of these technologies are going to be coming through at costs that make it very, very conceivable that you could have a much more dispatchable generation or load balancing across a grid. So hopefully we'll get to that when we have some questions, but I will throw it over to Giovanni.
What I want to say right away is, I mean, you know, this is incredibly exciting stuff. The question that I'll address to both of you later is what are the challenges of making this happen? So you just put that aside and think about it. But, you know, if you could pull off some of these things, you solve a lot of the problems we've been talking about as to the showstoppers as to why renewables don't work as well, or why energy costs are going to keep going out of control, and why we can't do some of the things we want to do in society. We're now fortunate enough to have Giovanni Santi, European Commissioner for Research Center for the Institute for Energy and Transport, and he's going to take a different slice on what the problem is that needs to be solved. Go ahead, sir.
Yeah, thank you, John. In fact, it's not that different. The situation in Europe is comparable to what the situation in the US and has this depicted also by Cheryl. The thing that we need to consider whenever we want to see how the energy will develop in Europe, that of course we need have to face with many countries, many different economic, industrial, and also situations, also different energy sources available in different countries. So European Commission, first of all, has to remain always neutral, technology neutral. But what we need to develop is a kind of rewarding energy market in Europe. We need to solicit integrated approach. We need to bring them together to leverage the investments to make a real European level project approach. Now, we do also have, this is why we developed the so-called Strategic Energy Technology Plan, whereby we do have two main avenues. One avenue, let's say, for the non-mature energy technology. So we do have the so-called energy alliances. So stakeholders are mainly university, research center, and they do need to look for how to bring this technology to a more mature stage. Right. I'm thinking, for example, to marine energy, or the fourth generation nuclear power plants, or the second, third generation biofuel via LNG, as it was already mentioned. Next generation, the so-called smart PV panels. So we do also see lots of possibilities, as it was already mentioned. However, we don't see any kind of silver bullet who will solve the problem. As also Secretary Moni said, we also look for an optimized mixture of different sources. This is the key solution for the future. Whatever option you might select, you will always need to see a good combination, optimized mixture of different energy sources. Of course, the final choice is left to the member states. We can never say which solution has to be implemented in Italy or France or Germany, But we need to develop a consensus among European countries how to develop a combined energy market. This is the key issue. Now, for the more mature technologies, we have set up the so-called industrial initiatives, where again, and we want to find, let's say, private and public money and resources to gain and to bring them more rapidly, more efficiently to the markets. And this is what we are going to do, for example, for photovoltaics, for wind, offshore wind, for this third plus generation of nuclear power plants, bioenergy. So even there, we do look for a plethora of solutions, not just one bullet point. But what I wanted to say now, for me, the key issue in Europe is how to develop a proper energy system. We are far away from being ready if we do shift from, let's say, substantially a vertical energy system where you have an energy source and then a distributor, to an horizontal system whereby the final consumer might be consumer but also producer of energy because of their little photovoltaics or wind system. Then you need to think to a completely different retail energy market, retail energy infrastructure. And this is what we call, if you like, intelligent smart grids, intelligent super grids. This is, in my view, the most difficult aspect to be achieved in Europe, again, because you need to put together 25, 26, 27 different countries to put together their own plans, their own structure, so there are legal, physical, and also financial barriers to be won. And this is exactly what we need in the future in Europe. In Europe, we do need to completely a paramount shift from the present energy system to the future one, whereby the consumer has a completely different proactive role, not just as a passive one, the last consumer, but again, the proactive role. We do need an intelligent way to understand how and when the energy should be delivered, where it can be also for storage. So it's a very intelligent new system that has to be developed. So this is why we are concentrating on this kind of integrated approach rather than one technology instead of another. This is at the moment, the key challenge in Europe.
Yeah. Thank you very much. I think you can see there's a lot of aspects to what's going to change the energy structure. And we never know quite where they're. I'm going to ask each of you to give a quick set of thoughts on what do you think are the biggest challenges you face in trying to figure out which of these, in your case, which of the technologies you want to focus on, and how do you get them in place? And Giovanni, I guess for you, it's a question of how do you get Europe pulling together on all this, and can you give us some quick feedback on that?
No, yes. It's an important question, right? I mean, we're funding very early stage research. I think an advantage that we have, the way we fund, about a third of our awards go to academics, about a third go to small companies, and about a third go to large companies, national labs. But every single one of those groups almost always has another partner. So we see universities and small companies, universities and labs. And we actually have in our process, from the first day of the award, a conversation about what happens at the end of that 3 years. And by having that conversation, you get focused on who has to be involved in moving this forward. Is it regulators? Is it the end consumer? Is it a manufacturer? Who's this going to matter to? What's going to get in your way? And by inviting that conversation over the 3 years, you build an ecosystem of thinking around this new idea so that as they move forward, some of the technologies will work better than others, but we don't know up front which ones will. So you have to run the first experiment. So all the horses start. But as they come around the last turn, you start to see some look better than others, but hopefully some other folks are now in the game betting and being willing to jump in to move these to the next step. Now, the thing that I worry most about, though, is how do we get that next stage of funding to happen? Like, if there's a value proposition, ultimately, somebody's going to have it as a large scale, whatever it is, a battery, an inverter, whatever it is. But in between, when we're still taking chances and we have to build a demonstration, where and how are we going to get that done? And so in the US, we've had a lot of conversations at the state level where the incentives might be different. Different large companies have partnered with us where there's a different incentive. But I think for me, that's the really tricky piece. How do we not lose steam inside a place where everybody's agreed that this makes sense to move forward? But what's the right way to make that next step? Absolutely.
Thank you. That's sort of what we call in the United States the valley of death. You've got the idea out there. You think you've got something that's going to work, but how do you get it financed into the next stage? Giovanni.
Okay. I think in Europe now, as you know, in a few days, we will finalize in the European Parliament the discussion for the multi-annual financial framework. And one of the few issue which has been strongly defended by the European Parliament was, from financial point of view, is exactly research and innovation. So we are going to launch this Horizon 2020 program, which is born to be about 70 billion euros. And the main target there is to, again, to solicit and to make possible to invest in research and innovation. So throughout the whole chain, from the very research to the market deployment, so going across the innovation and the death valley, which sometimes block good idea and they never ever become real industrial projects, via the so-called PPP, so the public-private partnerships.
Right.
If we will be able to leverage the investments from the member states and from the industrial sectors on very few specialized, however, very clear, identified, prioritized projects, which impact definitely the energy future in Europe, and they will solve societal challenges. This is the key word. We don't want to finance anymore one technology against another, because the risk that the return of investment is too far away from now, and the citizen won't see the advantage of that investment. We would like to see addressing clear societal problems so that the citizen will see the return of investment, and we are making them to work together. So if we do want to finance a project in the North Sea via offshore wind, we will not finance the development of advanced 10 megawatt offshore wind itself, but how this will be properly connected via long undersea cables, then how will be distributed, how will be energy stored properly, so the smart grid, again, the long distance transportation, the accumulation, so storage of energy, and finally we will solve the problem of that area in Europe, whereby we will have more affordable, cheap, and also, let's say, competitive energy. So this is the challenge we have in front of us, whether this Horizon 2020, again, with the money available, will be good in soliciting and, let's say, making possible an higher level of public and private money for these kind of integrated projects.
Okay. Well, that's fascinating because Europe, I think, is ahead of the U.S. in using public-private partnerships. Yeah. And it's one of the things that we've been holding some discussions on, because there's a lot of U.S. industry in the water industry and the energy industry where if we could figure out how to use public-private partnerships, which is not the same thing as taking a business and privatizing it, is something about building a coordinated approach between a public institution and the private investors in a way that serves a greater public good. And I think that's fascinating, and the U.S. needs to do a lot more work in that area. Dinu, I'm going to turn to you because one of the things that is interesting here is Dinu has got a whole new set of opportunities that he's been looking at, and I think you're all going to find them fascinating. And I think when we get through his presentation, if we have time, I'm going to open it up to the floor for questions, because I think many of you may have questions of all three of our speakers. So I'll go ahead.
We'll try to draw your attention to a more real project, not only on policies, and sometimes dreams about the future, but about something which is very, very real and can be developed quickly enough. The adventure on which this case study it's based started 7,500 years ago, just right here, across the street, in the Bosphorus, when the waters, salt waters of the Mediterranean started to flow into a sweet water lake,
Thank you.
which was at that time 30 meters lower, and we are calling it today the Black Sea. This catastrophic event created an anoxic basin in the Black Sea, under 300 meters below the surface of the sea. Everything is dead. It's one of the unique anoxic basins in the seas of the earth. And this created also an opportunity. A layer of organic mass which was formed by the dead life in the sea fell at the bottom and created a layer of organic mass, which it's a very young hydrocarbon, very young oil, if you want. But this very young oil can be transformed into useful energy and has also another unique property. It's mixed with nanoparticles of heavy metals, which were brought by the rivers into the sea. And we, at Marexin, which is a company dedicated to this research, tried to transform this substance into useful materials. I will pass the microphone to my colleague, Răzvan Popescu, which is the one of the managing directors of Marexin, to present you the technology which we have developed.
Thank you very much, Dinu. And let's start to have a look to our presentation. What are we going to see today? There are three different aspects that I would like to introduce in this presentation very briefly. One is the occurrence of the sapropellic mud in the Black Sea, extracting and processing the sapropellic mud by applying Marexin proprietary technology, and last but not least, the economic, social, and environmental effects of this big project. Well, Dinu has already started to introduce this topic to you, but I would like to emphasize that in 2008, the Romanian subsidiary of Marexin has obtained a license for exploring the Black Sea waters, the Romanian Black Sea waters. And within its limits, Marexin carried out and consolidated the exploration program in order to identify possible marine resources. Well, before going on, just a few words about the Black Sea, because Black Sea is really a remarkable sea within the regional seas. I would say it is really a unique sea in this region. And why this? It is almost cut off from the rest of the world's ocean. Its only connection with the Mediterranean is through the Bosphorus. And this 35 kilometers long channel, natural channel, has two water flows. One carrying the salted water from the Mediterranean to the Black Sea in the lower levels, and the other one returning a mixture of salted water and water from the Black Sea, so fresh water, and I will tell you why fresh water, on the upper levels in a higher volume. The Black Sea is considered to be the biggest meromictic basin, and for the one of you which are not familiar with this terminology, this means that the upper levels and the lower levels of the water do not mix together, if not every 1,000 of years. The reason for this is a different salinity between the different layers, and as a consequence, the different density of the water. About 88% of the Black Sea water, it is anoxic. Thus, we can see that we can consider the Black Sea as the world's largest permanently anoxic basin. And this is very important for the resource we are going to talk about. Here you have some figures about the Black Sea. I will not stop on all of this, but just to emphasize the maximum depth of 2,200 meters, which is important for our presentation, and of course the quantity of sapropel reserves, which is distributed all across the seabed of the Black Sea. Now, in order to talk about some more easy to understand figures, we refer only to the yellow ones, this 248 years extraction at 8 million tons a year flow rate project, and these are referred only to the Romanian jurisdiction. Now, we have briefly, Dinu has briefly introduced also how the Black Sea as we know it today was formed. And this is the post-glacial warming, so 7,500 years ago, increased the sea level in the Mediterranean, and this entered the fresh water of the Black Sea, which used to be a lake for more than 60,000 years. Now, here in this graph, you can see, sorry, but the pointer does not really work. So we have the depth of the sea. You see that we have about 2,200 meters, what I have mentioned before, and we have the hydrogen sulfide content, which increases with the depth of the water. Well, during this, let's say, catastrophic event, basically the high salinity deeper water became anoxic rapidly, causing a major crash of the entire deep ecosystem and killing all the oxygen-dependent life forms. And you can see here how this organic matter of the deep sea creature did not decompose in this anoxic condition, but they accumulated on the seabed as sapropelling mud. This is how this resource really was created. The sapropelling mud consists of 3 different layers. From top to bottom, we have the coccolith, which is a layer of high concentration calcium carbonate. We have sapropel, which has an organic content. And in conjunction with some nano-sized mineral deposition. And we have the bottom layer, which is called mineral muds. It is a layer of inorganic materials. During the exploration in 2008, Marexin carried out about 1,300 kilometers of sub-bottom profiling, 1,000 kilometers of high-resolution bathymetric surveillance, and 165 core samples have been collected and analyzed. We will see more in detail what the composition of this sapropelling mud and what the product mix will be extracted from this natural resource. But I would like to emphasize the total organic content of this natural resource, which is, as you can see from this graphic, is in between 7 and 15% compared to other well-known rich fossil soil rocks like the domenic shales, where the total organic content is in between 2 and 3%. Marexin has developed a process flow which fully unlocks the really vast potential of this unique resource. The extraction process, it is a quite complex one. and require the combined use of different existing technologies. And this is very important because Marexin has focused in developing and patenting a full process while using as much as possible existing technologies. This in order to minimize the risk when going from pilot scale to industrial scale extraction and then processing. So only some components of the technology were improved and patented according to our needs. Now, the extraction starts from the seabed by means of a subsea mining tool, and the slurry which is extracted is transported via vertical transportation system to a offshore processing vessel. On this vessel already the first part of the processing takes part because there is a dewatering step, there is a reduction of the water content of this sapropellic mud from roughly 85% to about 25% very rapidly, and the excess of the marine water is then returned to the seabed by means of the same vertical transport system that we are using to raise the resource to the surface of the sea. This concentrated resource is then transported to an onshore processing unit, basically to a storage tank, to a storage area, because this is going to function also as a buffer in order to grant a continuous production then onshore, and goes through other processes which are further concentration of this material, compacting of this material, and then, and this is also a very important part of the process, you have seen that this sapropellic mud contains an organic and an inorganic part. Well, these are processed in one single feed by meaning of an electric arc furnace, of a gasifier, and we have three first products obtained. One is the syngas, organic part. We have the inorganic mud, this mineral mud that is going to be further on processed. I'm going to show you some data about it. And we have the CO2, which is captured from both organic and inorganic processing. Due to the fact that environmental issues are very important for us in Marexin, one of the major challenges was to recover the CO2 and to reprocess it in order to produce valuable organic compounds and biofuels. So we close the circle. Now, for a better understanding of the process, I would like to show you a short video. It is a 1-minute video, and then we'll come back again to some of the equipments that are used in this video. Please. We are waiting for the video.
If it doesn't come on, you may want to verbally describe it. Oh, there we go. Is that it?
Let's see it like this.
Okay, good.
It's not the best way, but in any case, so this is the offshore processing vessel. Unfortunately, the picture is cutted. In the rear side of this offshore processing vessel, we have a launch and recovery system for the subsea mining tool. You can see it in the back. Here it starts the vertical transportation system I was mentioning in order to raise this natural resource to the surface and return the excess water. There is a system of centrifugal pumps that are helping us to perform this in a very fast way. Let's do not forget that here we are going 2,000 meters below the sea level. And this is the subsea mining tool with a suction mount in front of it. It is an Archimedes screw propeller crawler. Okay. So due to the fact that the video, so now it works, okay? Let's see it again. It's probably, it's 1 minute more, I'm sorry for this. So this is the launch and recovery system for 3 subsea mining tools I was mentioning. Once again, the vertical transportation system, which is made of 4 different pipes, 2 of them used to raise this slurry to the surface, 2 of them to return the excess water to the sea. Just to give you an idea, this whole process takes just a few minutes. We're talking about 7 minutes to extract the material, to bring it to the surface, and then return to the water to the seabed. And this is also very important. You see that this subsea mining tool is just kind of floating on the surface of the seabed. So it's like a fish which really swims on the surface of the seabed, extracting only about 70 centimeters of this sapropellic mud, which is what is interesting for our project. So let's move on. Just a short emphasis on the 3 equipments that I have mentioned: the offshore processing vessel, the vertical transportation system with the centrifugal pumps, and the subsea mining tool. Now, I was mentioning before that Marexin has developed a process flow which is pretty unique because it works in cascade, and we are able to really extract in a very fast way a marketable material, while the remaining material is going to become a feedstock for the further processing. These organic and inorganic matter are going in an electric arc furnace, then split into initial products, syngas and mineral-rich slag, which are then via a Fischer-Tropsch process going to ethanol, bioethanol, fuels, and the mineral slag finishing in metallurgical products and construction materials. Now, this is the result. This is a product mix for this indicative annual extraction rate of 8 million tons of sapropellic mud. Going from top to bottom, so from the bigger quantities, we are talking about 2.8 million tons a year of ethanol. And in the right side, you have also an indication of the major application for these materials. We are talking about 1.9 million tons a year of cement for the construction industry with a very similar quality to the Portland cement. We have about 1.5 million tons of precipitated calcium carbonate, also in this case, construction, but also for paper industry. We have about 800,000 tons of ferrosilicon alloys, reinforcer for steel. We have about 400 tons of aluminum, 160 tons of magnesium, 21,000 tons of titanium. And going back to the steel, you see that there are several other materials very important for this production, such as manganese, vanadium, nickel, and chromium. And last but not least, 170 tons of cobalt for superalloys. So you can imagine that this mega project will have really significant social and economic impact. And I would kindly ask Dinu just to finish this presentation with some information in this respect for you. Thank you very much.
Slide, and saying that 40%, as you see, of the revenues from the project are due to energy, and from the other 60%, about 50% are very precious metals. Because even if the quantities are small, like for instance for titanium, which is only 21,000 tons, the price of titanium today it's about $25,000 per ton, which makes a revenue of about 600 million per year from the total of 6.5 billion a year, which are generated by this project at a rate of 8 million tons a year. And I remind you that 8 million tons a year only from the Romanian part of the sea means 250 years of exploitation. If we speak about the whole Black Sea, and I will emphasize that Romania has only 10% of the resources, all the rest is split between all the other countries. For instance, Turkey has 6 times more than Romania. And will be able to exploit even at bigger rates. We calculated that the IRR of the project starts to be reasonable over 800 tons per hour as a rate flow, which means about 6 million tons. And we took the example of 8 million tons per year, which brings the IRR of the project, the internal rate of return, to more than 40%. Unleveraged. NPV 20 billion, CapEx 5.7 billion, and OpEx 1.1 billion per year. This, in Romania, represents, from the economic, social, and environmental point of view, an impact of something like 5% of the gross national product in comparable terms, and 66 direct and indirect jobs, 6,000 direct and indirect jobs. From the ecological point of view, this technology doesn't have an impact, a major impact on the environment, because the excess water is returned into the same anoxic basin, and the impact in the onshore part of the technology, it's also very limited because we are recycling the CO2. In fact, these are the 3 R's on which we are basing the technology. And we have no waste products. The waste, if you want, are the few million tons of cement and calcium carbonate which we are producing. It's bringing this technology because we are not speaking only about a resource, but about a technology to the stage of a unique opportunity, which is environmentally responsible, applies proven technologies. That's why I say it's real. I said at the beginning, and has a significant economic and social benefit for the region. In Romania, we passed the stage of the exploration, and the government approved the pass to the exploitation stage, and now we are negotiating the terms of the exploitation license with the government.
But you know, this is incredible. You know, it's what this story tells you, which isn't a story, it's an opportunity, is there's always going to be something that you don't anticipate. There's always going to be some big event that occurs that changes your thoughts on something. We've got, this one would radically change Romania's economics, Turkey's economics. It would also change the availability of fuel for this area. And it creates a whole bunch of new minerals that we weren't even anticipating out of such production. And I think the only reason I'm going on now is because we're already 10 minutes late, and the next meeting starts at 4:30, which I'm also leading. So I've got a problem of jumping between centers. But I think it's an incredibly fascinating set of information, which I really hope. Now I'm going to ask you one question, which I hope you can answer quickly. How close are you to being able to find this financially viable or support for it?
We think that after ending our negotiations with the Romanian government, and even during this phase, we will be able to put together the financial consortium to develop this project.
Right.
And we are ready for partnerships in the other countries to develop this. I didn't want to pass from reality to dreams, because I have to tell you that this has also a part of dream for the future, which is the gas hydrate.
Yes.
The sapropel has also a content of gas hydrates,
Right.
About 11 cubic meters of gas for 1 cubic meter of sapropel.
Yeah.
And this is securing the internal energy for the offshore part of the technology.
Okay.
But the mining technology can be easily translated to the gas hydrates mining.
Yeah. Okay. Well, that's fascinating, and I apologize to the audience because I would have loved to have allowed you lots of time to question the speakers, but unfortunately, I don't have that luxury. We got I think 3 fascinating presentations, and I would like to make sure we thank all the speakers and give them applaud for their. And I think what I encourage you to do, if you have questions on any of them, grab them in the hallways and make sure you have an opportunity to ask them, because they will be here. I think on both from all 3 speakers, there's going to be lots of other backup information that you may want to achieve. I have an obligation to also remind you, and I should have at the first, this session is on the record, and you are encouraged when you're in any of these sessions to tweet and using number AC Summit type hash sign, and that the next session begins at 4:30, which is 10 minutes from now, and it's going to be on energy efficiency and smart grid strategies in ballroom number 3 downstairs. And then in this room, if you want to stay here, there's another session on Eastern Mediterranean gas. I encourage you all to remember to keep your credentials on you at all times, because you want to bring all your belongings, including your headsets. And it's important to note that for tonight's dinner, buses start at 6 p.m. from the front of the hotel, and the ferry departs at 6:15 p.m. for those who don't get seasick at the front of the hotel. And if you don't make the ferry, you will have to take a bus that takes 1.5 hours. You do not want to miss the buses or the ferry. The ferry does have drinks, and the buses will leave promptly at 6 p.m. And you must wear your credentials to board the ferry or the buses. Buses will bring everybody back from tonight's event. I want to thank you all and appreciate your interest in this topic, because I think it's a big one. I think these are the things that are going to make it a different world for us as we move out. Thank you.